Okay, good morning, everybody. Okay, first let me express my gratitude. I'm grateful to Professor Alok and dear Gargi for giving me this opportunity to express my deepest regards and uh, gratitude to my Guruji, from whom I have learned, learned so profoundly that it helped me to navigate through my research career in a very effortless manner. So again, I would like to express my deepest gratitude to Professor A.N. Mitra. So let me say that it was Professor Mitra's conviction at that time. That means it means late 60s and early 70s, when he considered that quarks are fundamental particles, when most of the people didn't believe that these are fundamental entities. Now, this allowed us to do a lot of calculations of hadronic matrix element, which had deep implications for the quark model as well as the pattern model. In fact, I spent my time with Professor Mitra from 73 to almost 78 end. So I spent about 5 years with him. So see, one would say that his conviction, particularly uh, regarding his idea regarding that the nucleon is not only belongs to the eighth representation of 56 representation of SU6, it represent to it is a mixture of 70 as well as 56 representation SU6. This was very profound idea in the sense it allowed us to do a lot of calculations regarding hadronic matrix element, in particular about photohelicity amplitude and neutron charge radius, two very, very important. In fact, Feynman, just Dr. Dayanand Prashar emphasized, the Feynman was also interested in quark model. And in 70, he wrote a very famous paper referred as FKR, where he had emphasized the importance of helicity amplitude. In fact, using Mitra's idea, we were able to explain a lot of very difficult cases of this helicity amplitude, and that was really an important. Moreover, so neutron charge radius, neutron was a neutral particle, so understanding its charge radius was very difficult in those days. So we were able to, through Mitra's ideas, we were able to explain this neutron charge radius also. That was part of my thesis, apart from many other calculations. But very importantly, see, I use this idea of Professor Mitra's idea of this, what he called as mixed nucleon in what is called developing a chiral constituent quark model with configuration mixing. In fact, in the late 80s and early 90s, it was realized in the deep elastic scattering experiments that the valence quarks of the proton do not carry the entire spin. They carry only 30% of the spin. This was characterized as proton spin crisis. Not only that, there were evidence of strange quark and other kind of gluons and other things. In other sense, that the neutron and nucleon structure deep inside is very, very complicated. So we use this idea of mixed nucleon to develop this chiral constituent quark model with the mixed nucleon, and it was able to explain a lot of including this proton spin crisis as well as others. So we were able to contribute. However, see, after having learned many lessons from quark dynamics, I shifted to flavor dynamics. And in flavor dynamics, that's what I have been doing for the last two or more than 2 decades. And I would be discussing some aspects of flavor dynamics, that is phenomenological fermion mass matrix and flavor mixing. Now, basically, that's why there is slight change in my topic, and I hope the organizers would excuse me for this, because I found that my talk, it is not possible for me to cover both the aspects, work dynamics as flavor dynamics, in half an hour. I need at least more than an hour to explain both the things. So I decided that I would concentrate only on flavor dynamics. In fact, Nimai Singh is also very much interested in that, because we have been discussing about it on many occasions. So let me start with this. Can I go to the next slide? Yes. Okay, my talk would be, I will have some general observation regarding Fermion mass and mixing, then some pertaining to texture zero mass matrices, texture zero quark mass matrices, and texture zero lepton mass matrices. Then capital this compatible texture zero mass matrix with modular symmetry, which is a very latest, and then few concluding remarks. Okay, so let us, if you look at the spectrum of the Fermion mass and mixing, it's very complex, and that also shows that the problem is very complex. If you look at quark masses, they span almost, you can say that 10 almost 5 orders of magnitude. Then the quark mixing angles span another, you can say, 4 orders of magnitude. You can see that the Cavivo angle is somewhat large, then the next angle is much smaller than that, and then the next angle, mixing angle, is again very, very small. So this creates what is called the, you can say, hierarchy of the quark masses and the mixing angle, and it becomes little But if you add the neutrinos also, and you can see that the interestingly, the neutron mixing angles are large, or neutron oscillation angles are large compared with the quark ones, but their masses are very small. And the smallest mass could be maybe, you can say, 10⁻² electron volt or fraction of an electron volt. The sum of the masses, latest, you can say, sum of the masses given by this Planck experiment, which is 0.15. And if you consider neutrinos to be Majorana particle, then you have to add almost another 14 or 15 orders of magnitude. Now, if you look in totality, the neutrinos and the quarks together with Majorana neutrinos, it spans almost more than 25 orders of magnitude. So this problem is difficult from theory point of view also, as well as from the computational point of view also. And that is why there are not many attempts we try to discuss the problem in a comprehensive manner. That means quarks and leptons together, and doing, you can say, a consistent job of explaining both the spectrum. Most of the attempts are related to neutrinos, where the mixing angles are large, and then of course we do not know, we right now we don't have a you can say idea about the smallest neutrino mass. Okay, so the pattern of quark mixing angles and lepton mixing are very different, so that adds another you can say dimension to the problem.
Professor
So,
Manmohan Gupta, I apologize to interrupt you. Is it possible for you to kindly go full screen?
Hello?
Professor Manmohan Gupta, could you kindly go full screen, please, if possible?
I'm not able to get you. So in order to decipher the,
your
you can
display
communicate
is
to
not the
me
full
later.
screen. Your display is not the full screen. Please make it full screen.
I'm not able. Can you send message through cell phone?
Anyway,
Hello?
please go ahead.
Okay, so there are experimental refinements also, as well on theory also. A lot of approaches are there. We can characterize the approaches as top-down approach and bottom-up approach. Now, in the top-down approach, we have grand unified theories, string theories, and other kinds of theories. We try to, you can say, produce quark masses and lepton mass matrices, and then try to go further. But there is no, you can say, a theory which has a comprehensive, you can say, explanation for the vast spectrum of, you can say, masses and mixing angle, which I have just mentioned. So what the best thing is, there are, of course, ways to, you can say, some solutions. Okay, so the way we would like to understand this problem is, let us go to the standard model. And in the standard model, the quark masses defined like this and this. We will start with the quark masses. The leptons can be following the same pattern. So we find that the Fermion mass matrix are arbitrary 3×3 complex matrices containing in general a total of 36 real free parameters. For these matrices to provide valuable clues for developing an understanding of flavor physics, it is desirable that the number of free parameters gets constrained. Without loss of generality in the standard model and its expression with right-hand quarter singlet, Fermion mass matrix can consider to be Hermitian. It is through the polar decomposition theorem that any matrix, any complex matrix can be broken as a Hermitian and a unitary matrix, and a unitary matrix can be always be absorbed in the, you can say, right-handed singlets. These Hermitian matrices are characterized by 18 free parameters. Again, the number of free parameters are large. Therefore, to start the problem to handle this problem, so Weinberg implicitly and Harold Fritsch explicitly formulated what is called the texture approach. In the texture approach, some elements of the mass matrix are assumed to be zero, and then we proceed further with that. For example, in the Fritsch ansatz, this is how the Fritsch ansatz Mu and Md were assumed. And if you look at the structure, uh, a particular structure is said to be texture N0 if it has n number of non-trivial trivial zeros, that is the sum of the number of diagonal zeros and half the number of the symmetrically placed off diagonal zero is n. For example, this is texture 30 and this is texture 30. Together, they would be called texture 60 quark mass matrices. So this is how they started with reducing the numbers. No, the point is that if you follow this kind of approach and then try to calculate, and anyway, texture 60 was ruled out. But if you go to higher texture 50 and 40, the number of possibilities become very, very large. In fact, there are almost 576 quark mass matrices which have to be individually analyzed and then try to see whether someone follows the data or not. So therefore, this approach has its own limitation. So we decided that we should try to proceed further in a more general manner. So what we did, these are some of the publications on which my rest of the presentation is based. There are some review articles, including one by us, and there are two by Harold Fritsch and Zing. So then these are some of the latest papers on which our presentation. Now, if you, we try to use what is called a weak basis transformation. So the standard model allows a weak basis transformation without any loss of generality. So if we can take a unitary transformation and apply it on both upside as well as downside mass matrices. Now this doesn't no, a weak basis transformation, the gauge currents remain same and the CK matrix would not change, but there would be some changes in the quark structure. So it has been shown that the weak basis transformation, like you have a unitary transformation W, which acts on both the Mu and Md, and using this transformation, it has been shown that the mass matrix can be either in this form or in this form, where this is shown by Fritzing, where the 1, 3 and 3, 1 element is both zero, the all other elements are non-zero. We follow this approach. It is because using this approach, we can have exact diagonalization of the mass matrix. So now the weak basis transformation preserve hermiticity as well as you can say that one doesn't have to deal with large number of possibilities. One has to deal only with those possibilities which are compatible with the weak basis transformation. So that is what we try to do. Now, this is very general. There are no constraints. So if we start with this kind of mass matrices, we can proceed further for doing the calculations. And see this zero at this point, it can be at this point also, and it can be at this point also. Like this is what is mentioned, that we can have 0 at 1, 3 or 3, 1, 1, 2, 2, 1 or 2, 3. So they are all possible cases. So this increase some of the cases, somewhat, there are 4 possibilities of cases, but not beyond that. And then, of course, there are other possibilities related to the basic 4 possibilities. Now, what we do is that in order to, you can say, simplify the calculation, what we do is we constrain the parameter space available to the elements of this mass matrix. One can consider the following hierarchy: natural mass matrices for the elements of mass matrix, as shown by Pichai and Wang, Gupta and Ahuja. So in fact, Pichai and Wang had shown that there has to be some constraints on the elements of the mass matrix so that you can say it remains compatible with the CK matrix. Otherwise, if you violate these, then it becomes very difficult for the mass matrix to be compatible with the CK matrix, which is again hierarchical. So if we calculate for doing it, I would not get into too many technical details of the calculation. The way we proceed is we separate the phases and the real mass matrix and then go ahead with the you can say we construct the you can say transformation diagonalizing transformation. No, diagonalizing transformation has some implication in the sense that there are square roots, so they have plus minus sign. The phases have to be chosen in a very carefully selected manner. Otherwise, it becomes difficult to follow, and then this becomes mutually exclusive. The other possibilities of phases do not fit the data, so they are ruled out. So we have chosen those kind of phases, and then the CK matrix is constructed, and then of course we use this Quark masses at the MZ scale, and then of the Quark mixing parameters, or you can say CP violation parameters. This sin to beta represent the CP violation, other of course the normal three mixing angles. So we, unlike Wolfenstein parameterization, we follow different parameterization. We believe, and we have written one or two papers also, that the PDG representation is more suitable for when unitarity has to be preserved, unlike the Wolfenstein parameterization, where unitarity has to be proved order by order using the parameter lambda, which is the Cabibbo angle. So if we continue with this thing, and the parameter 5 and related phases of the Quark have been given full variation, EUED have also been given as with the condition of naturalness, and then we construct this matrix. And then obviously this is fully in agreement with the PDG, because there are a good number of parameters in the theory, so it has to agree with the PDG representation. So therefore, our next step is, no, what about, this is the mass, these are the mass matrix. You notice that of course, this CP violating J comes out in the right amplitude. I should also mention something about this J parameter. In fact, back in 1999, we were the first to calculate this J parameter, and using very raw data, we could predict, and that prediction still is valid. Of course, it had larger number of errors. I talked to Cecilia Jalskog also, and she was also quite impressed. Somehow or the other, it is not neither mentioned by PDG nor by many other people who work in this area. But we were she acknowledged that our paper was much earlier than many other papers. So we introduced that this J parameter is very important for calculation of CP violation effects in this CKM paradigm. See, if you look at the mass matrices, this element 1, in both is very small. So obviously we wanted to see whether if we ignore this element and proceed further, what is the effect of that? To that end, for example, first we try to see the, like if we plot this EU and E. EU, E is this is the first element, and we find that with respect to sin to beta and Vs, we find that the dependence, there is no dependence of VUS and sin to beta on EU. That means if we ignore this element, hardly it will make any difference to the calculation. So we ignore for both MU and MD this element and then redo the analysis. And what we find is that the CK matrix again comes out to be right. The CK matrix, the values agree very well with the, you can say, PDG data. Therefore, what we have done, we have reduced the number of parameters from texture 20, we come down to the texture 40 mass matrices. Now, if we are texture 40 mass matrix, then obviously there are other representations, other possibilities which we have to consider. So there are 4 possibilities. This is 1, 2, 3. First, we have already considered. So these other elements are related to permutation symmetry, which is a unitary matrix, so it does not have any independent consequences. So out of the 6, we have to consider only 1 also. This we have already considered. Now, this line, if you look at it, the third generation is decoupled. And if you have a decoupled third generation, we will not be able to reproduce data. Therefore, again, this can be easily discarded. The other two categories, 2 and 3, we have done the analysis, and what we find is these are also ruled out in the sense that if you look at the VCK matrix, the VCB value comes out very large in both cases. In fact, this is the graph also shows this thing. The VCB value is much larger than what is the current expected value. Therefore, these 2 possibilities are also ruled. Hence, we are left with only one possibility, which is very near to the what is the Fritsch-like mass matrices, where if you look at it critically, what one finds is that except the 2 element, the other structure is similar to Fritsch-like. But see, this is as far as the phenomenological analysis is concerned, we have not been able to show, nor anyone else has been able to. This is the only unique possibility. We are still working on it and hoping that we'll get some clue. And later on also I'll mention that discrete symmetry and modular symmetry may provide some clues in this direction. The same thing can be carried out for the texture zero lepton mass matrix. There are a lot of analysis, large number of papers, mostly you can see in the flavor basis. In the flavor basis, we take the ML and the lepton mass matrix to be diagonal and a neutrino mass matrix to be non-diagonal. But we have tried to consider using quark lepton symmetry, that if at all we have a theory which predicts both quarks and lepton, there has to be symmetry between the two. So if we try to consider the Hermitian 2-0 and 4-0 quark matrices and try to and assuming neutrinos to be Majorana particles, we have carried out the analysis and some very interesting results have come out. I will not try to get into you can say too many results, discuss too many results, but I'll just mention some very important results which we have obtained with this analysis. So this is of course the PMNS matrix, which is really reproducible. Now what we find is that in the case of if we consider the inverted mass ordering and the normal mass ordering, the predictions are very different regarding the what is the element MEE, that is which measure the you can say the possibility of neutronless double beta decay. And what we find is that in the case of inverted mass hierarchy, there's no, it's almost as far as the these are the phi's, and if we calculate this is of course the smallest quark mass matrix. Then if we vary with the M3, then the result do not change much. So this is the prediction of the, you can say in the case of inverted hierarchy. But if you go to the, in the case of normal hierarchy, what we find is the results are very interesting in the sense that there is a dependence on the phase factors also, that is a CP violating factor, as well as no, this is the smallest neutron mass, M1. Now, what we find is up to this point, that is for M1 from 001 to 0.1 electron, the bond on parameter 1 gets sharpened on 1 obtains Me within the band. This is the, no, if the neutrino mass is in this range, then we get, this is the MEE value. And whereas for M1 greater than this, this value, 0.01 electron volt, then one finds that there's a broader spectrum. So the predictions are very clear as far as the element Me is concerned. This is for texture 2.0. But if we go to texture 4.0, no, there is a very sharp prediction. And that prediction is, you can see that the M1 and Me is confined to very small. So I am sure that in the, in particular, careful comparison plot showing parameter Me for texture 2.0 and texture 4.0 normal ordering reveals that the case later one obtains very limited region of viability. Texture 4.0 shows very limited region of viability. Therefore, non-zero values of one elements, the neutron mass matrix has to be significantly different predictions as can. See, in the case of neutrino, we cannot go from texture 2.0 to texture 4.0 because the one element has a lot of dependence. And it is because the neutrino mass spectrum is very different. So therefore, we can't go from 2 to 2, 4, 4. However, if we assume that the one element is not there, and that is why the predictions become very sharp. So if by any theory, we are able to show that the quark mass matrices as well as neutrino mass matrices of texture 4.0, then we have very sharp predictions and which can be easily, which is going to be tested in the coming, you can say this is the further range of lightest neutrino mass severely constrained. So this is the range of the lightest neutrino mass M1 in the normal hierarchy if we have texture 4.0 lepton mass matrices also. So we have used this is as far as the this quark mass matrix is concerned, and quark mass matrix is considered unique viable option description of quark mixing data. And for neutrino, there is a prediction for Me, for NO as well as for the normal hierarchy as well as for inverted hierarchy. Now, see the next question. I have not gone into details of that. Now, obviously, the next question arises: how do we, you can say, reproduce this quark or texture specific mass matrices? There are a lot of attempts including discrete symmetries. So in fact, we have also worked on S3 cross Z3 model, but somehow or the other, it is not easy to reproduce the model. However, a similar kind of model one is able to get. And of course, that model is able to fit the data, but I am not including in this. But lately, what we find is that modular symmetry lately has given a new gateway for explaining this fermion masses and mixing. Now, this has some inherent advantages, and modular symmetry, I will not get into the details, and we are still working on it. We have not arrived at any specific texture structure, but we are almost near that. And this, I'm sure that those who are working on it, they understand how this modular symmetry is defined. And then, of course, this is how we obtain the y functions, and this is the gamma functions. The gamma function, it corresponds to, for example, the modular symmetry incorporates discrete symmetry, like gamma 2 is S3 and gamma 3 is A4. So a lot of analysis being done using this gamma 3 and A4, gamma 2 S3. Also, we are particularly interested in S3 cross Z3 model because we had some experience with doing calculation in the using the discrete symmetry of S3 and Z3. Those calculations are still we are doing. No, this is that means this is compatible, and this is the structure which we get using S3 cross Z3, and this is as far as this is compatible. This is again texture 2.0, so this is compatible. I am sure that we still have to carry out a detailed analysis of that because there are some issues. I am sure there are some issues about what is called this is Dedekind function. See, the numerical values of Dedekind function I find is different given by mathematician, by string theories, and as some people who have tried to use this fermion masses and mixing. So their values are not coinciding. We are working on that what is the best value to be used for the calculation. Only then there is some kind of, you can say, emphasis in the calculation. No, so there are some advantages of modular symmetry. I think the most important is that this is directly from mathematical framework, dimensional compactification of string theory, hence is more reliable than any other existing theory. Or in other words, it is very much compatible with the string theory. So therefore, whatever predictions one makes in this modular symmetry, I think the other important factor is that the hierarchy is built into the y functions. And that is very important. The y function, the symmetry has already hierarchy in it. So one doesn't have to add what is called flavanones, or you can say additional, you can say scalar particles to provide a hierarchy in the fermion mass matrix. So anyway, I have covered some ideas, and with this, I would like to conclude and again re-emphasize that the lessons learned by a smaller person like me from Professor Mitra's interaction, they were really profound, and it has helped me in not only uh, getting into new areas, but keeping me always active, taking inspiration from you. I remember that even about I think about a decade back or maybe earlier than that, I had met him and still working, and he was publishing papers. And I remember that he had mentioned that he had written a paper on three body forces. So his mind was active, he was physically active always. So I always long to have that kind of inspiration instilled in people like us so that we keep working and keep enjoying his legacy. Thank you very much for listening to me.
Thank you, Professor Manmohan Gupta. It is almost 30 minutes, but we can entertain one question at least as a
Yeah, sure.
representation. One question at least. Yes, please, sir. Please. No sound. You please put us.
Second,
Oh, yes.
this modular symmetry seems rather ad hoc. What is the dynamical justification for that?
Yes, right.
Could you, Dr. Nemaisi, repeat it because I'm not able to hear him.
No. I will repeat. Modular symmetry used in neutrino physics is ad hoc. What is the justification?
Again, I am not able to. And maybe you can mail this question. I will send the reply maybe today itself. So
Yes,
you can send the question to me through mail, or
yes.
Nemaisi, you can send through this WhatsApp message also. I will
Okay,
send through email, right?
you.
I think there
Thank
is
you.
some problem about audio at my end. So that's why I'm not
So-
able to hear others that well.
So by
Can I
using
ask a question?
Okay, I think the best thing is that I've almost utilized the time. So whatever questions are there, they can be mailed to me. I'll send the email reply to either Nimai Singh or I will send it on the WhatsApp, right?
Okay, sir, Professor Haridas, is it okay?
Fine. Wonderful.
Okay, now it is time up. So let us give the thing to the next speaker.